Good morning, students. We are learning water resource engineering and hydrology. We were discussing about hydrological parameters, and in today's lecture, we will talk on the methods of calculating average rainfall all over an area. In the previous lecture, we have talked that the rainfall is not equal in each and every region. There is a variation in the rainfall. There is a variation in the rainfall over the areas. Okay, so it is mandatory to calculate the average rainfall over a particular area. So the session we will start with the topic is the methods for calculating the average rainfall over an area. So rainfall recorded by a rain gauge that represent the rainfall at particular station. Okay, now in many hydrological studies, the average depth of rainfall over a specified area due to a storm is required, and for determination of such average precipitation over the areas, a large number of rain gauge has to be plotted. Okay, now the average rainfall over an area can be computed by three different methods. The first, that is arithmetic average method, Thiessen polygon method, and isohydral method. We will start with the first one, that is the arithmetic average method. Well, if there are small variations in the rainfall values, those measured by the different stations that we have plotted, this method we can use the average depth of rainfall over an area that is obtained by dividing the sum of depth of rainfall that are recorded at different gauge stations, and those are located in the areas by the number of stations. Okay, so if we say that the different precipitation, okay, that is P1, P2, P3 at different rain gauges, or we can say that this P1, P2, P3 are the particular depth of rainfall that we have recorded from the rain gauges, and we have n number of rain gauges station, then the mathematical equation of this method would be P is equals to P1 plus P2 plus P3 up to Pn divided by n, wherein obviously we have discussed that P1, P2, P3 are the depths of rainfall that are recorded, and n is the number of stations. Well, there are few merits and demerits of this particular method. Well, this method is a very simple method. It is used to determine the approximate rainfall. If the rainfall is uniformly distributed over the whole catchment, that is rarely possible, but at such cases, this method gives the best result. If you are observing that in the whole catchment the rainfall is uniform, we can use this method. Well, in the hilly area or in the hilly terrains, also this method can yield fairly satisfactory result. If the number of rain gauge stations are more and the variation of the individual record is not far from the mean, then this method is to be taken to get the accurate results. Well, the method is rapid and has it got excellent adaptability for the computer process. It is also a very costly method, and it is very difficult to install the maximum number of rain gauges in the particular catchment for the better result or the accurate result. So these all are its merit and demerits. Now if we move on to the second method, that is the Thiessen polygon method. Well, in this method, the rainfall that recorded at each rain gauge station is given a weightage on the basis of area which it represents. This method is better than the arithmetic mean method, which gives the equal weight to all the stations. With this, we have a mathematical formula that is P average is equals to P1 plus A1 plus P2 A2, P1 A1 plus P2 A2 plus P3 A3 up to Pn An upon A1 plus A2 plus A3 up to An. Whereas this A1, A2, A3 are the area represented by these stations, and P1, P2, P3 are the rainfall at that particular rain gauge stations. With this we can get the rainfall at particular station in the particular catchment area. Also, this method have few merits and demerits. So let's talk on that. Well, in this method, results are accurate than the arithmetic average method. Rainfall, those recorded at each rain gauges, is given a weightage on the basis of area which it represents. Okay, this method eliminates error due to non-uniform distribution of rain gauges. If the catchment area is very large and the rain gauge stations are also quite large in the numbers, then this method can be adopted for the computer computation. If stations are few compared to the size of area, then Thyssen polygon method should be used. This method does not consider the orographic influences. That is the limitation of this method. Now we have seen arithmetic average method and Thyssen polygon method. Okay, so based on these two methods, let's solve one example. So the example is saying that find average rainfall by using two methods, that arithmetical average and Thyssen polygon, and for that we have this data. We have total 5 rain gauge stations. Okay, in each rain gauge station, here we have precipitation and we have area of the polygon. So here we have at the first station we have precipitation in centimeter, that is 13. In the second rain gauge station the number is 18. In the third 29. At fourth station 25, and at fifth station 15. Okay, if we talk about the first method, that is arithmetical average method, the equation, that is P average is equal to P1 plus P2 up to Pn upon n. Here we have total 5 different stations. Okay, so our n would be 5 and we have 5 different precipitations in the data. So that 13 plus 18 plus 29 plus 25 plus 15 whole divided by 5. If we sum the P1, P2, P3 up to Pn, we will get the value as 100, and it should be divided by 5 as we have the total number of station is 5. So the final answer would be 20. That 20 must be in the centimeter. Now we will solve this example with the Thyssen polygon method. In the Thyssen polygon method, we have a formula, that is P1A1 plus P2A2 up to Pnan divided by the sum of area. Okay, now here we have P1 as a 13 and its respective area, that is 160. So we will multiply, or we will make a product of precipitation and the area of polygon. That will be 13 into 160 plus 18 into 172 plus 29 into 165 plus 25 into 205 plus 15 into 185 divided by sum of area, which is given. Okay, so we have the final answer as a 20.13 centimeter. So here you can see we have an accurate result as a 20.13 centimeter with respect to the arithmetical average method. Okay, so this is how we can solve the example for calculating the average rainfall over an area. Now also we have to discuss about the third method, that is the isohedral method. In isohedral method we need isoheads. Now isoheads are the contours of equal rainfall. So an isohedral map that showing the contours of equal rainfall that represent a more accurate picture for the rainfall distribution over the basin, over the catchment basin we can see. Okay, now here we have one mathematical formula, that is P average is equals to sigma A into P1 plus P2 divided by 2 whole divided by sigma n. So this is a mathematical equation wherein again A1, A2, A3 are the area and P1, P2, P3 are the rainfall at particular stations. If we talk about the merits and demerits of this particular method, this method is most suitable for hilly regions and rugged regions. If the analyst has the knowledge of orographic effect on that particular region, he or she can use it in the constructing the isohedral map for the better results. This method permits the use of all available data. Now, overall, this method is superior to the other two methods, that is arithmetical average method and Poisson polygon method. So now we will discuss one another example that is based on this isohedral method. Okay, the example is saying that estimate the average depth of precipitation over the basin for a drainage basin of having 600 square kilometer area. Now here with this we have to estimate the average depth of precipitation. Okay, so that is the average rainfall. Well, we have this data. Now here we have the catchment area and different isoheads. Okay, we have the formula, that is P average is equals to sigma A into P1 plus P2 upon 2, okay, upon sigma A. So here first of all we need area individual, and the second thing, that is the product of area into P1 plus P2 by 2. So for this we need to make a table. Okay, here we have this table wherein we have plotted the isoheights, we have catchment areas. Now this is the individual areas. Now we have to find the area between two different isoheights. So for that, at the isoheight of 35 we would have the catchment area as 35. At 40 it's the initial state, that's why the area would be 0. Okay, at the next step the area is 35. Okay, at the isoheight of 30 we would have the area between two isoheights, that is 90 minus 35, so that would be 55 centimeter. That would be 55 square kilometer. At the 25 it would be 150 minus 90, so that would be 60. At the 20 isoheights it would be 310 minus 150, it would be 160, and so on. So here we have the area between two isoheights. Now the next step that we have to find, that is average rainfall. What is average rainfall? That is P1 plus P2 by 2. Okay, and that we have plotted here. So the first P1, that is 40, the next is 35, and the average of these two, that is 37.5. Again 30 and 35, the average is 32.5, and so on. Now at the end what we need? We need a product of area into average rainfall. So that is 37.5 into 35, and the answer would be 1312.5. Okay, so with this we have made a table. We have the value of area into P1 plus P2 by 2, but we need the value of sigma, means summation of the product of area into average rainfall. 12,575. Now if we substitute this value in the equation, we will have P average, that is the average rainfall or the average depth of precipitation, as a 20.96 centimeter. So this is how we can calculate or we can estimate the average rainfall over an area. We have three different methods: arithmetical average method, Thiessen polygon method, and isohydral methods. Okay, now the next thing that we have to learn, that is the optimum number of rain gauge that we required. And for that, first we have an equation, that is the n, which is the optimum number of rain gauge that is required. N is equals to Cv upon E raised to 2, that is the square of Cv upon E, wherein Cv is equals to coefficient of a variation of rainfall and E is equals to allowable percentage error in the estimation of mean rainfall. Okay, so the value of coefficient of variation of rainfall, that is 100 into sigma upon P bar. Now the next question that arises, what is sigma and P bar? Okay, so for that, sigma is equals to the standard deviation and P bar is equals to average annual rainfall. That data would be given, but we have to find out the standard deviation, and for that we have this equation, that is under root of sigma P minus P bar square upon n minus 1. So this you have to remember, and with these steps you can find out the optimum number of rain gauge that we require. So here we have an example, okay, that is in a certain river basin there are 4 different rain gauge stations. That means we have n is equals to 4 with the normal annual precipitation amounting to 800, 520, 450 and 319 millimeter. Now we have to determine the optimum number of rain gauges in the catchment if it is desired to limit the error in the mean value of rainfall in the catchment to 10%. That is the value of E. Let's see in the example. We have the formula of N, that is Cv by E square. Now the first step that we have to follow, that to find out Cv. For Cv we need standard deviation and P bar. So starting with the sigma, okay, for the standard deviation we need P minus P bar. So before everything we have to find out the value of P bar. So P bar is equals to P1 plus P2 plus P3 plus P4 upon N. Okay, here N is equals to 4. If we substitute all the values that are given, we will find the value of P bar as a 540 millimeter. Okay, now the next, after P bar we need to find sigma P minus P bar square. So P, that is the individual rainfall or the individual precipitation, those are given as a 800, 520, 450 and 390. If we substitute the values in this, we will find the value of sigma P minus P bar square as a 98,600. If we substitute this value in the sigma formula, that is the standard deviation formula, we can able to find the value of standard deviation, and that would be 181.29 millimeter. Now here we have sigma, we have value of P bar, so we can find the value of coefficient of variation, that is Cv. So 100 into 181.29 divided by 550, we will have the value, that is 33.57 as the coefficient of variation. Now we are at the end of the example. Now we can find the value of optimum number of rain gauge, as we have Cv and E. So Cv is equals to 33.57 and E is the mean value of rainfall in the catchment area, that is the 10%. Okay, so that we have substitute over here, and After that, we have the value is equals to 11.26. So there is no possibility of having 11.26 rain gauge. So we will connect it with the nearby values, and that is 12 numbers. So according to this data, or as per this data, we need the optimum number of rain gauge stations are 12. Okay, I hope student you understand this topic deeply. Thank you so much for your kind attention. We'll see you in the next lecture.